Welcome to today's class. We shall be talking about introduction to artificial intelligence. Okay, so artificial intelligence, like the trending topic, the trends going on in this era of Industry 4.0 is the automation of activities we normally attribute to human thinking and rationality, such as problem solving, decision making, and learning. AI lives within the intersection of many classic disciplines, including philosophy, neuroscience, behavioral economics, mechatronics engineering, and that is our own specialty, computer science, and mechanical engineering. Okay. So, what does the philosopher say? They say, where does knowledge come from? How come some are knowledgeable than others? Then the linguist says, how does language relate to thought? That's natural language processing. Okay, the neuroscience says, how do our brain process information? Okay, what is the rationality behind that? The behavioral economist says, how do you make decisions to maximize utility? The mathematician says, what can be computer? And the computer science says, how can we build an efficient computer? So what are the research areas we'll be looking at today? We'll be looking at the machine learning. This will be an introductory class. In our next class, we'll talk more of introduction to machine learning. We'll introduce robotics, inverse and forward kinematics, and we'll dive into all of this in detail in our next class. So, machine learning, expert system, computer vision, natural language processing, and robotics. Let's take it further. So we say machine learning is the science of empowering machines to make decisions without human intervention. Okay? It's the learning of computer algorithms that improve with experience. Learning of computer algorithms that improve with experience. So machine learning, we have three, or let's say four types of machine learning: the supervised, the unsupervised, the reinforcement. We'll take this in detail in our next class. Going forward, expert system. Expert system is an artificial agent which leverage pre-programmed knowledge to offer advice to make decisions in its simplest form. We can think of an expert system as a computer complicated decision tree or nested if then statement. If Y and X and W happen, then we instruct the computer to do Z. So if this happen and this happen, then do this. The clinicians, the doctors, they use expert system a lot to predict, to diagnose some diseases, An expert system can take advantage of human insight discovered through trials and error. Expert systems are more predictable and are less likely to make extreme errors when faced with previously unseen inputs. Expert systems have historically been faster and easier to implement through machine learning, though machine learning becomes more accessible in recent years. Okay, so going forward on expert system, we say, why do we use expert system? Why do we develop expert system? One, because human experts are short and limited in supply. Now to employ maybe qualified engineer might be expensive. So instead of that, you just use expert system. Of course, not in all situations. Another one, expensive to develop or hire. How to get a hold of one in a hurry. Okay, let's assume you want to know if you have malaria or if you are pregnant or this and that. You can just look at this expert system that have been developed to just predict what might be wrong with you. Can be lost due to retirement. Of course, women can be lost due to retirement, change of job, relocation, or death. Expert systems serve the following functions with respect to expertise: document, reproduce, teach, and of course, another reason why we develop expert system is that computers don't get tired, they don't get bored. Okay, so I have three ways why we implement expert system. Now, where does this knowledge come from? Okay, we say human experts, doctors, lawyers, engineers. The extraction and formulation of knowledge derived from various sources, especially from human experts. Okay, so human experts over time, doctors, lawyers, engineers, we can get then other sources such as social media, documented book research reports, etc. So, components of an expert system. We have three components of expert system. We have one, the knowledge base, the inference engine, and the user interface. What do I say? The knowledge base, the inference engine, and user interface. These are some expert systems that have been developed, like mycin. It helps the physicians to diagnose certain bacterial disease, like prospector, produce where certain mineral deposits can be found. Okay, and Dendra. These are some expert systems that have been developed in the past. Let's start from knowledge base. Knowledge base is a database that holds specific information and rules about a certain subject. We can view the knowledge base as a collection of objects and the attribute. This is the object and these are its attributes, okay? An attribute is a specific quality that with its rules help us to define an object. I'll take for example, the object can be represented as follows. So this is an object. The object is dog. What are the attributes of a dog? It's a mammal. Okay, it lives on land. It does not live in water. It's a domestic. It is being used as a pet. Okay, then come back. I will go for going forward. We'll see how this expert system is being constructed using the if and then statement. Okay, what are the attributes of a lion? It's a mammal. It lives on land. It's not domestic. Cannot be used as pet. It can roar. Okay. How about hippopotamus? We said the attributes. It's a mammal, of course. Lives in water, not domestic, not used as pets, cannot bark. So these are the attributes and these are the objects. Now, inference engine. Inference engine is the main processing element of the expert system. The inference engine makes use of the information in the knowledge base to reach conclusion for different situations. Considering the knowledge base as a collection of objects and attributes, the inference engine attempts to use this information that has been gathered in the knowledge base from the users to find an object that matches it. So we have the deterministic inference engine, the probabilistic inference engine. My focus here will be forward chaining and backward chaining, because we can go deeper into this in another class, looking probably on expert system. Then we are using Python programming, one of the packages in Python program for our expert system. So construction of expert system, we look at the forward chaining and the backward chaining. So forward chaining, inference by forward chaining. This method is called data driven, whereas backward chaining is called object driven. So data driven, this is because it starts with an available data and uses inference rules to extract more data until a goal is reached. Okay, and inference engine using forward chaining search for inference rule until it find a rule where the antecedent is known. That's why I say forward chaining is data driven, where backward chaining is goal driven. So forward chaining uses information provided by the users to move through a network of logic and or until it reaches a terminal point where it's which is the object. Now look at it. Is it a mammal? Yes. Not used as a pet. If I say yes, then definitely it's no longer a dog, because dog is being. Is it a mammal? Yes. Not used as pet? Yes. Not domestic? Yes. In this partner, we are no longer considering dog. Dog is out of it, because dog is domestic. Cannot bark. Dog can bark. Yes. Lives on the land. If I say lives on land here now, that rules out the hippopotamus. But I say lives on land, yes. If then it's hippopotamus. Based on the available data, I know that it's hippopotamus. Let's take another example. Do you have headache? Yes. Are you stooling? Yes. Are you coughing or something? Yes. Do you have a bitter tongue? Yes. Then you have fever. If I now go forward, are you vomiting and all? Yes. Then most likely you are pregnant. I'm just trying to give an example. This is why about backward chaining? Like I said, is the object driven or goal driven. This is the reverse of the forward chaining and is sometimes called the object driven. It starts from the goal and works backwards through the antecedent to see if there is a data available to support the chosen goal. It starts with a hypothesis and request for information to confirm or deny it. So an illustration. So I just say you come around to me and I say, oh, you have fever. So after I've already assumed that you have fever, then I start calling out the attributes. Are you stooling? Yes. Do you have headache? Yes. Do you have loss of appetite? Yes. Then you have fever. Or let's say I just want to diagnose your car. Your car breaks down. Then I say, oh, the fuel in the car or the engine is bad. Then I can now start, is the car smoking? Yes. This and that, I call some attributes from the car. Then I say, oh, based on that, the engine is bad. So that is backward chaining. So now I start from, it's the dog. It said, how do you know it's a dog? Is it a mammal? Yes. Is it domestic? Yes. Then it's a dog. So if after I say it's a mammal, yes, and I come and lives in water and say yes, then it rules out this. It can no longer be a dog because dog doesn't live in water. Okay. So let's look at it's a dog. It's a mammal, yes. Does it live in land? Yes. Can it be used as pet? Yes. Can it bark? Yes. Then surely it's a dog. Look at this. It's a dog. Is it a mama? Yes. Lives in water. If you say yes, then it rules out being a dog. Then it is not a dog. Then I go for lives on land. Yes. Not domestic. Yes. Not just as pet. Yes. Can it roar? Yes. Then based on this, it is not a dog but a lion. So that is the difference between forward chaining and backward chaining. So I have a table here, difference between forward chaining and backward chaining, like we've explained. We say one is data driven, the other one is goal driven or object driven. You start with facts in the knowledge base. You start with a user entered a goal to be proved. So for backward chaining, just tell me what is wrong with me, then you start calling out the attributes, okay? Inference rules are applied by matching facts to the if parts of the rules in the knowledge base. Inference rules are applied by matching the goal to the then part of the rules in the knowledge base. Result is new facts added to the knowledge base. Result is sub-goals to be proved, okay? So these are the differences between forward chaining and backward chaining. I will stop there for expert system. Moving forward, another major research area in artificial intelligence is computer vision, okay? So we've talked about expert system, we've talked about machine learning. Then computer vision. We say computer vision is the automatic extraction, analysis, and interpretation of images or video. Computer vision converts photos and videos into numerical arrays, enabling machine learning algorithms to draw inference, which makes prediction and even generates new images based on user-defined inputs. Look at this image of a street. Then, of course, we are trying to get analyze, extract, and interpret this image. Potential use of computer vision have been studied for decades, but computer vision has only recently become possible at scale thanks to three innovations: more efficient algorithm, that's deep learning and all that, better computing resources and availability of images to train with. Okay, so a particular instance of computer vision is that we might try to look at, okay, let this computer predict if I'm wearing this green color or if I'm wearing this yellow color. And I can say, okay, whoever doesn't have this blue color cannot come into this place, so I can feed my computer to know what a green color is, what a yellow color is, okay? That's computer vision. So these three innovations have opened the floodgate for new computer vision use cases, including self-driving cars, okay? Of course, to be able to navigate, computer vision has been used in this area, and automated retailers, as cameras, lidars, and other special sensors become less expensive, then we'll find ways to elevate many of our most inefficient processes using computer vision. We are now trying to say now that computer vision will develop with time. Okay, we will not go deeper into this. In our next class, we will talk more on computer vision and we'll pick all the research areas one by one. Going forward, we'll just look at robotics, and of course, robotics is one of my home major area. I specialize more in robotics and automation, process automation. So we'll have more classes on robotics, forward kinematics, inverse kinematics, could be polynomial, robot trajectories, and all that. So I just have definition here. We will not go into details in this class on robotics. It is the science of designing, constructing, operating, and applying robots to solve human problems. Of course, we'll define robots, we'll go deeper into types of robots and all that. So this is it. But what is the future of robotics in artificial intelligence? We are trying to look for a robot that has emotion. That's where humanoid comes to place. A robot that you can date. People say men has come, women has come now. So we are looking for robots that, of course, that have empathy. So this is what brings about empathetic robots or emotional intelligence in robotics. Okay, I say can be seen as how the system processes emotion, focusing on how input is translated through an algorithm to an output. So we'll not go deeper into this. Going forward now, we'll talk about natural language processing. So like I said, today being an introductory class, two major focus is expert system and natural language processing. Machine learning, we have a lot to learn on that. So in the course of this class, we'll be talking more on machine learning and more on robotics. Okay, so natural language processing. I have the natural language processing is the automatic extraction, analysis, and generation of human languages. Natural language processes pass sentences in various ways, splitting by words, splitting by letter, reading both left to right, reading right to left, to automatically draw inference about the writer's meaning and intent. So in natural language processing, we're looking at, of course, the spell check, let's say Grammarly and other software that have been developed. Grammarly, we're talking about the Siri. When you just say, Siri, play me this and all. How does the computer know how to interpret this. That's because of natural language processing. Or let's say you are online, you are just querying all like that. Oh, I want to learn how to do this, and computer is responding to you intelligently. How does it happen? That's because of the advent of natural language processing. So we'll look at, okay, I have the people we have for queries on the website, our smart systems, the calls we make over internet. None of them are actually human. So if they are not human, how come they sound so intelligent or think so human-like? Or how do they respond, okay, so intelligently, or are they well articulated? That is because of natural language processing. Okay, so okay, again, I have the definition as the branch of artificial intelligence that give the machine the ability to read, understand, and derive meaning from human languages. What are the steps involved in natural language processing? So, okay, examples of natural language processing. You don't know how to spell a word, autocorrect, like I said, autocorrect helps us in our Word document. You need to know if you have a copyright violation. Grammarly helps us to search through the web, etc. Then our Siri or Alexa on our smartphone, that is natural language processing. I said that before. How is data generated from our everyday activity, from social media, and all that? That's how we get this data, okay? So what are the steps involved in natural language processing? So the steps involved in natural language processing, one, say segmentation. Segmentation, which is to break this entire document down into its constituents. You can do this by segmenting the steps along its punctuation, like full stop and comma. Another step is tokenization. For the algorithm to recognize the sentence, we break each word into its constituent word and store and explain it individually to our algorithm. Bear in mind, in the course of this study, we'll be using more on Python programming, so and the packages that come with it. So these are theoretical part of it. This is like introduction class. Going forward, we'll be using more of Python. Okay, so tokenization, we take each word as a token, feed it into our algorithm. Another one is top words, the non-essential words, words that even without them being used, it will still make a meaning. I would use a sentence as an example. Another word is stemming. For our document, we can explain it to the machine. We can start by explaining to the machine that some words are same without their prefixes and suffixes, such as keeping. Okay, you can say skipping still means keeps, still means keep. They are all same. Okay, for non-English speakers, let's assume our brothers from India, China that don't speak more proficient English. Sometimes when they use this English, they might take off this prefix or the suffix. Okay, so skipping, you can say engineering is same as engineer, engineers, etc. So lemmatization, of course, we also identify the base words to different word terms such as mood, gender, etc. So when we try to remove the prefix or the suffix, sometimes it goes to an incorrect form. Let's assume disagree. When you remove the prefix D-I-S, it goes to agree, and you actually not mean the same thing. Let's say caring. Someone is being caring. When you remove the ing, it goes to car, and car is different from caring. You know. So lemmatization takes it back to the more correct form. Okay. Speech tagging. Now we explain to our computer the concept of noun, verbs, and other parts of speech to the machine by adding the tags. The last step here is the name entity tagging, which we introduce to our computers the everyday names by flagging names of movies, important personality, locations, organization, time, expression, medical codes, etc. that are not naturally known. Let's assume you are trying to tell your computer now that let's assume you're trying to tell your computer that Nigeria, and Nigeria is not on Google or internet. So Nigeria is a country in Africa. Okay. So now let's take this example. Now I have this example. Now Khalifa is the president of the engineering body, highly endorsed by Ekok and Ramat. That is my example. I'm listing this as Khalifa is the president of engineering body, highly endorsed by Ekok and Ramat. So segmentation will be the first one. One, I segment it into two different constituent sentences, which are one, Khalifa is the president of the engineering body. That is one. Another segment is highly endorsed by Ekok and Ramat. So I've been able to segment it into two different constituent sentences. The first segment, Khalifa is the president of engineering body. Second segment, highly endorsed by Ekok and Ramat. Another one step is tokenization, which I take it and feed it to my algorithm as a token. So now, how many tokens now? I say Khalifa is the president of engineering body. Now we have one token Khalifa, one token is another token B, another token president token 4, 5. So in this case now tokens 1, 2, 3, 4, 5, 6, 7, 8. So token is equal to 8. Okay. Token is equal to 8. Okay. So the next step is stop words. Stop words are words that even when they are being removed, they still make meaning to the computer. So now I have Khalifa is the president of engineering body. I can remove is D of B. So this becomes, so what such as this? So it becomes Khalifa, president engineering body, which is still very accurate. Okay, Khalifa, president engineering body. So after that, I do the stemming. Stemming, like I said, the prefixes and suffixes is being removed. So in this case now, engineering can go to engineers. Yes, engineering can go to engineer. Okay. So in this second sentence, I can say I can go to I. Endorse, endorse. Sort of, okay? So stemming, so we remove the prefixes and suffixes and still tell the computer that even without the prefix and suffix, these words are still the same. Of course, lemmatization now, like I explained before now, words that are being removed and doesn't make meaning, lemmatization return it back to its meaningful word. So output of lemmatization is a proper word. For example, a lemmatizer should map going and gone and went into go. Okay? So lemmatization is letting us know that going, gone, went, they are all same. Even though stemming, we might not be able to do that. So stemmer might incorrectly map caring as car, like I explained earlier. Caring and car, which are different things. The car is a vehicle. Caring is someone being showing care, showing concern, which are different things. So lemmatization takes about that. No. This caring is not car. It's actually showing care. So speech tagging. In this case now, and I explain this sentence. Khalifa is the president of engineering body. I explained to my computer now that Khalifa is a noun. It's a name of a person, okay? Is a verb. D is an article. President is a noun. Of is a preposition. D is an article. Engineering is a noun. Engineering body is a noun. So I explained this concept of noun and all to my computer, okay? So another thing is the name entity tagging. So let's assume now that I say Khalifa is the president of engineering body in Madagascar, for example. So if Madagascar is not known, I just say, okay, Madagascar is actually a country in so place, and any other thing that is not known, let's assume I say Khalifa is the president of the Jew. Let's say, okay, who are the Jews? Jews are the people who does this and that. So I explain this to you, and if there's any other thing that is not known here too, any other big name, any other location that is not known, I explain it to my computer. So these are the steps involved in natural language processing. So I have this question for you to answer. I say, which of these techniques is used to obtain words from sentences? This. Okay, so I'm sure you know the answer by now. Okay, another question: what is the difference between lemmatization and stemming? Support your answer with an example. Okay. So definitely, you know the answer because I've explained that. My third question will be explain briefly the 7 steps of natural language processing. So of course we have the segmentation, we have the tokenization, we have the stop words, we have the stemming, we have the lemmatization, we have the speech tagging, and we have the name entity tagging. Okay. So this will be the end of today's class, where we've been able to talk about the 5 research area of artificial intelligence, the natural language processing, which we've talked extensively on. Going forward, we'll use a Python program, of course, to know how this algorithm is being written. Yeah. So we talked about machine learning, which we'll go deeper into in our next class as well. We'll talk about expert system. We'll talk about robotics, and of course, computer vision. So these are the 5 research areas as mechatronics engineer that we will have to look into in artificial intelligence. Thank you so much for today's class, and I hope to see you next time. Bye-bye.